Hi everyone, how are you doing? Uh, Can everyone hear me properly?
Yeah.
Yeah, I can hear you.
Okay. Today we're going to be having a seminar on robotics technology and research. And today we have a guest speaker who is Ray Didinsky, currently a senior engineer at Apple, and also our mentors. She'll be presenting on robotic sensing systems, visual recognition and processing, safety management of autonomous driving at intersections, optimization of drone flight plans, and how students can conduct
哦，
individual
这
research.
个
Okay, I think these are pretty interesting topics. Ray, are you there?
Hey, yeah, thanks for the intro. Can you hear me
Yeah,
okay?
okay. Yeah, we can hear you great. Feel free to take over now.
Awesome. Okay. Thanks for that intro. Let me share my screen. The thing. Can everyone see my screen?
Oh, yeah,
I
we
can
can
see
see
it.
you now.
Yes, it
Hooray!
works now.
Thank you for the technical support, folks. Awesome. To actually kick things off here, today I'm just going to talk about a couple of robotics projects that I've had the opportunity to do and some of my research while I was going through school here. Um, brief introduction into me, I guess. I am from Arizona and have a partner and a dog. We now live in Seattle. And I'm working currently actually on the Vision Pro team. Anyway, I'm on the Vision Pro team. And it's basically a headset for virtual reality and mixed reality opportunities. And for fun, I like to go rock climbing and take my dog for long walks. Up in the top right is just a hot air balloon from the Air Balloon Festival that I got to go to. So I do like to travel a little bit. And that's the Arizona state flag. So I thought that was a cool one. Anyway, that's me. And today, just to get things rolling here, wanted to talk about some research projects that hopefully folks might find interesting here. So the first research project that I'm going to touch upon is sensor meshing within optimizing drone flight. And then the second research topic I'm going to talk about is the autonomous vehicle intersection management problem. And there's both simulation as well as actual physical testing in the real world using RC cars in the latter project. And so I've thrown this word around now, and you might be wondering, what is a cyber physical system? Well, you all have gotten to work on them all through the year. We see them every day. It's basically a system that contains both hardware and software components. And oftentimes it requires real-time requirements. So you have to actually have feedback into like what is going on in the real world so uh, practically speaking, when we are implementing or using cyber physical systems, there's usually two phases to actually like rolling out a solution to a problem, right? The first is via simulation, and then actually being able to use real world systems to model or even like end to end prove out your cyber physical solution. And so one of the first system example that I had mentioned previously, which now we get to dive on into, is this unmanned aerial vehicle, which is basically a hobbyist drone vehicle. And what we were posed with as our research question was whether or not we can improve flight accuracy using sensor redundancies. And by sensor redundancies, we mean sensors that might do the same thing, but come up with slightly different results. And can we use all of these different inputs in order to make our flight even better? Um, and so maybe to kick things off, why don't we start off with a brief little exercise? I maybe we can all come up with a couple of sensors that we think would be useful to build redundancies into a drone or even an airplane. Um, I don't know if people want to come off mute and maybe shout some stuff out. I can
GPS.
chat. What's that?
GPS.
GPS. That's awesome. Yeah.
LiDAR for crash stuff.
Yeah. Yeah. LiDAR. That's a good one.
Barometer.
Barometer. Yeah. These are great.
IMU.
IMU. Yeah. That's a really good one. Anyone else want to
Do
take
you
their
need
stab?
to somehow detect if one of the rotors is like failing somehow?
Yeah. Yeah. Like error detection. These are awesome. Anyone else? Well, you all basically nailed it on these sensors. And maybe our list here of the sensors that we actually chose to use might sound a little bit like all of your lists. Um, so, what we actually ended up trying out for our testing here were these series of sensors. And over on the right, you actually see the drone that we ended up building out, which uh, you can see even some of our individual parts here. So the main body consisted of the LiDAR, which you can kind of see on the front, which is like the two pistons. Um, and then the altimeter is actually right there on the main body as well. Um, uh, you got your rotors, which are all connected into your flight control board to manage the air detection, which is another good call out that we had. Um, we did not include GPS. And for uh, a couple of reasons, um, the, the GPS module would be really good for um, if we had a really high quality GPS where we could have very precise uh, uh, control over where or insight into where we are, right? But most of the like off the shelf GPS modules that you can buy don't kind of have that level of precision. And so for something like flight accuracy, it ended up being too expensive to really dive into it on our student budget. So
You
this is what we went ahead with our sensor meshing, and what our like base proposal of trying to do was, can we just get this to fly across grass at a consistent um, height in kind of like a U formation? And what ended up happening was this. Oh my gosh. I was about to say, there's some moody music here. You can kind of see the drone is doing all kinds of things in terms of its like height modulation, which is not what we wanted to happen. And that's why we thought we had all these sensor redundancies, but at the end of the day, it just didn't end up working out. And there could be a variety of different reasons here. It could be that our sensor meshing or this kind of weighted algorithm wasn't properly refined. And just like a weighted algorithm, if you will, is kind of a way for you to take multiple inputs from one position, like altitude. You could use an altimeter and then an ultrasonic sensor pointed directly at the ground. And one might be saying it's 3 meters, one might be saying it's 2.5 meters. And you take the difference between them and say, okay, the altitude's 2.75, for example. So it could be that we were saying this sensor is more important than this other sensor, and that was incorrect. Or that some data points needed to be thrown out. It could even kind of tie back into this idea that a cyber physical system is so real time that maybe even our data points were out of date on some of the readings that we got. And so we were just meshing completely with the wrong data. But what we kind of boiled this down to is we hopped straight into the actual physical build and passed over simulation. Like we probably could have ironed out some of these weighted algorithm issues or throwing out the bad data points. and coming up with kind of a better algorithm for uh, determining the height if we had gone through and really thought about all of this in a kind of more um, formalized simulation. So uh, one big old learning there to stash into our pockets, which enabled us to kind of do more, I think, on our future projects here, which we'll talk about in just a second. But before we even dive into that, I wanted to take a moment to kind of call this back to our greater purpose, right? Our greater purpose was whether or not we can come up with a sensor meshing algorithm that improved flight accuracy and like can sustain the same height basically or same altitude while it's flying across. And so I wanted to pose this as more of an exercise of like, okay, we had a drone and we used this drone to model this problem. And I thought maybe what other problems can we possibly solve with robots? Because robots, at the end of the day, are tools. And like, what can we actually use these tools to help us understand and solve about our everyday world and cyber physical modeling in general? So I wanted to maybe let everyone have a minute and then maybe we can shout out some ideas that we came up with at the end of that minute. Sound good? Okay, cool. With that break, let me know if you have any questions about the exercise that we're going through here. We're at our minute. Does anyone have a cyber physical problem that they've come up with that they think robots can help us solve?
Someone in chat suggested to for making mapping.
Yes, nice. Do you want to elaborate on how we could? I don't want to call. If you want to elaborate in chat, feel free. We can always come back. But like, what could that robot do to make maps? Scan the surroundings. Yeah, that's awesome. And make YouTube videos. Yeah, so we can have robots that scan the surroundings and make maps and then can turn that into YouTube videos. It's great. Anyone else?
I'm still a little confused by the question. What does it mean to model a problem using a robot?
Yeah. So one way to think about this is so for our previous problem, we were saying, can we use all of these sensors to have a drone fly at a consistent height? And you can say that's even more open ended, where you can say, can we create an algorithm that allows something to fly at a consistent height? And the drone was our way of modeling that problem, saying, oh, we're going to use this robot to prove out that this algorithm works. So it's more like you're trying to use a robot as a means to an end. Maybe this will become more clear. I can just hop into the next portion And maybe we can come back to this at the end of that. So, for example, one thing that I guess I had in mind when I was posing this question was um, working with autonomous vehicles. So I did my thesis on autonomous vehicle research, but it's the issue with autonomous vehicles is I did not have an arsenal of autonomous vehicles to say, go, model this algorithm that I've come up with, because I was a broke graduate student. um, and so what we ended up doing was we used RC cars as our autonomous vehicles and created a 1/10 sized model to model this problem of how do we help autonomous vehicles safely navigate through an intersection. So I guess going back to the previous slide, if we were to, show navigator. If we were to use a robot to solve a problem that otherwise couldn't be solved, like a scaled problem, this might be a bad question, but what kind of modeling can we do with robots to help us understand the cyber physical world? I guess was what I was getting at. But if we were, we can maybe mull that over, keep it in the back of your minds. Is like this was the idea, right, of both cyber physical system example 1 and cyber physical example 2, is that we didn't have an airplane to say everything is fine because it'll fly at this consistent height. Just going to deploy it, Boeing. You trust me? No, I had to throw it on a drone so that I wasn't crashing a real life plane. Likewise, I'm not going to throw a bunch of vehicles through an intersection and say this is just going to work. Trust me with your vehicle. Graduate professor. So we had a bunch of RC cars that helped us model this problem. Which I will get into. But before we get there, we learned our lesson from research problem number 1 and said, great, research problem number 2, we're going to do a bunch of simulations now. And these simulations are going to not require us to have any physical hardware setups, because that is a lot to get through iteration after iteration after iteration, prone to bugginess, all of those things. And so you're able to iterate much more quickly, right? There's also robustness that you get out of testing, where you can say, okay, I've proven my algorithm works. I've run thousands of simulations, and this is what happens, especially with autonomous systems, right? Where you kind of have to simulate what they would be like in their actual world, where there's not as much oversight. So robustness testing becomes really important. And then you get to examine even larger scenarios with these simulations, rather than, oh, I built out 10 RC cars and look at them go through an intersection. I can say, no, like, look at this highway that I've simulated, and how we're able to make all of these vehicles go through the intersection on this highway safely. So that's kind of the pros of the simulation. That's what we did. Proved out our algorithm in simulation, and then said, okay, we are ready to start testing in real life. And so we built out these RC cars to do that. Because again, I wasn't going to ask my professor for the keys to his car. I was just going to build out a bunch of RC cars. If they crashed into the wall and burned, it was fine. So these are the sensors that we are using for this autonomous vehicle. It's very similar sensors: cameras, IMU, GPS, LiDAR, ultrasonic sensor, with a big one being the OptiTrack motion capture system. So I don't know if there's any gamers in this room, but the OptiTrack motion capture system is this it's like a it's how they create video games, where they basically put a bunch of markers, trackers all over people, and like use that to help model what the physics of this game is going to look like. And we kind of abused that system and said, what if we used this as our intersection that knows all about the cars, that communicates with these cars, and knows their exact positioning. So we used it to determine the exact positioning of where these cars were. So highlighted here are the actual markers that you have on each individual car. And this is what the system tracks. The OptiTrack cameras track these markers so that the system has exact positioning of these cars. And so that's what we primarily used for our positioning. So we went through a couple iterations of hardware testing. This was still a new system to us. How do we send it coordinates so that it knows the exact place that the car is supposed to be? This requires not only like the onboard sensor inputs from the car themselves, but it also required the exact positioning from the OptiTrack motion capture system. So we had to find a way to basically ensure that the position that the OptiTrack system was sending would go back into the car, and then the car would know, okay, I'm here and I need to get here. And how do I get there? And what's the safe route to get there? So we went through a couple of iterations of kind of that feedback process, that cyber physical process, right? Of I have a position and I need to actuate based on the position that this sensing system gave me. And you can see how crazy some of these iterations got, right? Like if you look at the overall loops that these cars are making, the trajectory isn't smooth, right? It's kind of jagged, it's all over the place. And eventually you get to this point where, oh, we have the smooth curve. This is exactly what we were going for. Yeah. And the way that that was achieved was via that like a tight iteration loop, and truthfully, like even derivatives, right, that were derived on a curve that like back to your pre-calculus days of identifying positions based on where you are closest to a point on the line, and that's ended up being kind of our basis solution. And so once we had a very consistent way of telling the cars a trajectory to take and those cars actually actuating on that trajectory, we could build on that and actually start to answer the research question, which was how do we model these cars to cooperatively navigate around each other in an intersection? And this again calls into this idea that there's kind of best case times and worst case times, and some cars might be faster than others. And how do we make sure that this fast car doesn't intercept with this really slow car and cause a crash in the intersection? And so that with all of these edge cases and our meager setup for modeling it, this essentially kind of boiled down to what you see on your screen here, where we had a manager that we called the intersection manager that says, we're going to speak to every single car, and we know every single car's best case and worst case response to what we're telling it to do. We know every car's best case and worst case speeds that they can go through this intersection. And therefore, we know the points at which these cars are going to potentially overlap if we schedule them with this much time in between. So it kind of was an effort to say, in the worst case, this car responds really slowly and moves really slowly. And in the worst case, this other car might speed up and hit it. But how do we make sure that there's enough buffer between these cars that they're not going to overlap? And so we came up with this algorithm that said, no one's going to hit each other because we've done all of the calculation. The cyber physical buffers are created such that each of these cars has a basically green zone, yellow zone, and red zone around them that says, as everyone's going to operate within this green zone, we guarantee it because this is a physics problem at the end of the day. And as long as everyone's operating in this green zone, there aren't going to be any crashes. And so we went ahead, and this is the cars running around the track, kind of more testing. Um, this is cooperative interactions, where if cars veer in and out of lanes, we're promising that if they stay in their green zones, they're not going to run into each other, even around turns, around curves, etc. Um, Trying to merge into different lanes. There's might be a fast lane and a slow lane. Um, and we say this is kind of a separate interaction that we want to make sure that everyone is able to stay within their green zone. And so this was modeling that kind of green zone mentality. I think that's it. Um, so once we had showed the reliability of everyone staying in their green zone, we had to show the robustness of this by actually modeling the intersection. And so to model the intersection, again, we used RC cars, all of the normal setup that I had mentioned earlier. And what you see here is kind of those green zones applied to the intersection. So each of these cars is going through the intersection. It's talking to the intersection manager that's saying, it is safe for you to go through the intersection. You've requested that you're going to turn left or right, whatever it is. And here's how we're going to schedule you such that you don't hit anyone else in the intersection. This is your green zone. You've told me your green zone. So I know exactly what will cause an accident. I know what won't cause an accident. And so this is your scheduled time. This is how long you have to get through it.
Is the promise of this to like reduce traffic?
Yes, reduce traffic. It's also in a fully autonomous system. So this is where every single car in the intersection is fully autonomous, has full capability of talking to everyone. And so there's different philosophies of how this is approached. One is more of a centralized approach where you talk to someone who knows the scheduling of everyone going through the intersection and can schedule you. Um, and this would be what's typically called a client server model. There's also a peer to peer model where all of the cars talk to each other and schedule through an intersection. And this, so this would be, I need to talk to 10 other entities to understand how I'm going to traverse this intersection. So it's a little forward thinking in terms of its research impact, if you will, in that we're not close to a fully autonomous system. But posing these questions earlier on is kind of hopefully going to help us understand how we're going to see the future progress. And so proving out both the cooperative system and the client server system, where you're talking to one centralized system that knows exactly where everyone's positioning is, are just two separate approaches to kind of this problem.
So was that the peer-to-peer model then, or the
Um,
client server one?
this one is a client server one. So this is one where you talk to an intersection manager. The intersection manager is that server that knows everyone's green zone, and is able to traverse intersections and is able to tell cars how to traverse intersections based on whatever their request is. Maybe they want to turn left, right, straight. Intersection manager can say, go this velocity at this time, and I guarantee you won't hit anyone.
Okay, so if I'm understanding this correctly, so we have a server that is controlling everything. Every car has buffer, the yellow zone for any latency in requests, I'm assuming,
Mm-hmm.
and they just maintain their green square. Is that it? And the green
Yep.
square just moves around. Okay.
Yeah, exactly.
So I have one question here, really. Uh, so like technically, how frequent are the cars sending the signals back to the server?
It would all depend on the level of traffic, right? So in simulation, um, we can get this up to highway speeds of like 70 miles per hour, traversing like a 5-lane intersection, for example, going one way. And how that scales compared to other, even just like normal traffic light systems. The, I guess, main benefit of an intersection manager and generally a fully autonomous system compared to what we have today would be that you can have cars going every direction without red, green, yellows, because the intersection manager can say, it is safe for you to go straight right now at this speed at this time, because of all of the other, I know exactly what all of the other cars are doing in the system, and I know that it's safe for you to go. It basically acts as its own police. I'm getting off track a little bit. Did that answer your question?
Yeah, I just want to get some high-level idea of how the system works in real time.
Yeah. So there's trade-offs between using this versus using like a roundabout and multiple simulations, right? The real world one I showed you, of course, was just RC cars. And I think the max that we hit for that was like 5 miles an hour or something like that. So, you have to apply the scale. And of course, with scale comes this larger buffer, if you will, of a best and worst case scenario with your latencies, etc. So yes, there's lots of cyber physical issues that continue to crop up as you scale this to larger systems, faster systems.
So I noticed that in the video demo that there were still cars like stopping. In fact, the stopping seemed to get worse the longer the experiment ran on.
Mm-hmm.
Is there like is that just because the server, everyone started like leaving the green zone or what?
Yeah, I think it depends at certain parts in this video. Of course, when you have more dispersed traffic, um, it's easier in some ways to not have stoppage. But if you have basically like 5 cars coming in one direction, all requesting to go any direction, really, this is where you get into um, slowdowns, yeah, like awkward timings. Um, as well as like if you arrive and someone's going in the direction that you've requested to go, like this, where you have like 3 different cars that are requesting to go in opposite directions, it's kind of where you get into your pileup situations. So it does and this is also kind of somewhat the drawback of we just had all of the cars go through the intersection and loop back around, which almost creates a queue, if you will, of cars that are waiting to in line to go back through the intersection. So by having all of the cars turned in one direction, you have everyone come back around the same direction, and it hurts their latencies, right? And makes stoppages happen as they go through the intersection as well. So all of these things to say, think about your simulations, even your real world ones, right? Because it still doesn't perfectly model your system. Are there any other questions? Well, with that, I leave you with just a handful more learnings. In that
There is a question in the chat. How much does it cost, that system?
this system in total, so we were lucky in that we had access to this OptiTrack system, which alone is a very expensive system to have. The cars themselves, though, each one of them's like maybe 50 to $100. So, as you create more, this of course gets cheaper and cheaper, which is kind of nice. So it's really, yeah. It's a cheap simulation compared to all of the vehicles that we would have had to outfit with all of this sensing technology, as well as coming up with how we're going to actually have an intersection in real life that all of these cars can just traverse every single day. That land alone and the land allotment would be kind of difficult. So it's within means for graduate student, but by no means is still cheap because of this OptiTrack system particularly.
For that OptiTrack system, why because in FTC robotics they usually install odometry wheel on robot and track each robot, right? Like
Mhm.
why use this OptiTrack system? And the second is that for that system, how often it can refresh and see or the car moves? Like is it every second or every 0.1 second can detect the position accurately?
Oh yeah, this is like millisecond accuracy.
Wow.
Um, yeah, so it's really, really fine grained tracking information that you can get from this, which is its main advantage. The reason that we used a system like this is because with you modeling this problem, going back to this server client idea, um, the server has a bunch of positioning information, and that's one of the foundations, I guess, that we laid our problem on. We said the intersection manager, this server, has knowledge about each car's position and can help tell it how to safely navigate an intersection. And so we kind of likened this to what the OptiTrack system could do for us, um, where we said the OptiTrack system is kind of the same thing in a lot of ways of like it has all of this fine-grained positioning information. And so it was a very one-to-one thing for us to be able to say, we're going to say the OptiTrack system is going to be our server, telling us exactly what the car is doing.
Makes sense.
So we also have a question from the chat. If everything is connected to one system, would the optimal scenario be that the distance between two cars always remain constant, so there would be zero traffic? Is that the cost function we're aiming to? We're aiming to solve here, Ri?
Yes, in some ways it's about no traffic. It's about how do you mitigate the um, latency everyone has going through an intersection, basically the traffic. How do you mitigate traffic and how do you safely traverse an intersection? And the safety harkens back to kind of this like green yellow zone of like this is these are buffers that we build around each car's position that as long as they stay within their buffered range, that's acceptable. But in terms of mitigation of traffic, you if everyone, for example, is going through an intersection at 20 miles an hour, you could say that there's no traffic in that system, right? But if there's a car that's capable of sneaking between two cars that are going 20 miles an hour at 40 to go its particular direction that it needs to go, it would be optimal for the system to be able to say, here's the 20-mile-an-hour car. It just snuck through the intersection. Oh, this 40-mile-an-hour car, though, can squeeze through these two 20-mile-an-hour cars that are traversing and safely not impact anyone else's schedule. And that's where the advantage, I think, of this comes in, where ideally, yeah, every single car can go 80 miles an hour through a system, through an intersection, and that's that. Like everyone has the same exact specs, so it doesn't really matter. But in actuality, what's probably going to happen is there's going to be 10 different autonomous car creators that have 10 different specs. And so, how do we incorporate all of those different specs into one system so that everyone can have the optimal experience from it? Does that answer your question?
Yeah, I think that's a good point. So basically, I think it's how we define the cost function of the system, right? Because obviously the highest priority is safety. Like there shouldn't be any collision. But
Yes.
beyond that, then what we optimize for, right? We optimize for maximized speed for all the cars or maximize speed for some of the cars or like fast cars go fast, slow cars go slow, something like that. Yeah.
Yes.
It's interesting to think in that front.
I would think that if you're having all cars maintain their speed through an intersection, Modeling that would probably be like very difficult on like the best case to worst case like response like we have here, right? Because the worst, there's like no margin for error at all there.
Yep. This is the difficulty of modeling safety, right? Where your buffers for your worst case just become astronomically large. Um, and this is additionally where you as a researcher have to put some bound on this, right? Where it's like you have to say, okay, all healthy operating vehicles. So you can't say, oh, a vehicle blew its tire in the middle of an intersection, therefore we'll still model everything to be safe. Like this is, I think, one of those moments where you put bounds and say, no, everyone's probably guaranteed to at least be capable of 40 miles an hour through an intersection as a baseline. So totally hear you. I think worst case for something like this can be very, very bad, but bounding your problem so that it's approachable, and then building on it for those blown tire situations are kind of where you would, I think, would want to go. Are there any other questions? Well, I think we kind of touched on a lot of these learnings already, but to wrap it on up here, um, I think it's important to chunk these real world problems and kind of work up to the real world solution. And thinking about robustness, you have to break it into bite-sized chunks. How do you validate basic assumptions, and how you build confidence on those basic assumptions so that you can continue to build your solution. Then once you kind of have your solution, start thinking about your edge cases, your blown tires, your um, those those things that you hadn't initially thought of when you proved this out, and making sure that it still doesn't break your solution. And with that, that's really it, folks. Any other just general life questions, project questions? Awesome. Well, it's been awesome talking to you tonight. Thanks for bearing with me and for all of the awesome questions, uh, and for the super valuable feedback too. This was great.
Well, we actually have still have a question here.
Oh, perfect.
Right. So we're kind of starting with the RC cars traversing through the intersections, right? And in terms of the research project, for that specific project, were there any like follow-up efforts to bring this to a more like physical, more real world, like with like not real cars, but with like larger things at a higher stake, right? Because robotic RC cars, if it's collision, then not big deal, right? Isn't anything that's like go beyond that or a little bit more serious?
Definitely. And this, of course, is not by any means us saying this is wrapped up, all solved, but more of a building step to say we've proved this out in simulation, we've proved this out on a non-jeopardizing system. Where else can we put this? And there's actually, ironically, a small fleet of autonomous buses in Michigan, that my particular lab that I was a part of is partnering with at this moment. And they've preserved an intersection in this tiny town in Michigan or something like that, and are like building out this solution. So slightly higher stakes. Still don't want to crash the buses, but building up to that real world problem. I also want to say, I guess, going back to kind of this client server versus peer-to-peer model, there's also a good amount of research being done into this peer-to-peer space, because the feasibility even of saying there's going to be at every single intersection an all-knowing server that knows positioning and can help you go through an intersection maybe isn't as feasible either. And that's where the feasibility of the cooperative talk to everyone that's going through this intersection, and make sure you're not going to run into any of your friends kind of is really powerful. So I know my lab, as well as other labs, are also investigating kind of more the cooperative peer-to-peer approach of cars talking to each other.
Okay, yeah, sounds good. That's a very interesting part.
When you build this simulation, it's also a real world simulation. Have you has a team ever tried to build a simulation in the software? Because that will be also you don't need any hardware thing, right? If you only test the algorithm.
Yeah, yeah. For testing out the algorithm, we actually built a full simulation in MATLAB, and I didn't have the files saved on my personal computer. They're on a school account, so just didn't have the time to pull those in. But yeah, that's kind of what a lot of people have been doing for this simulation. It's just, at least from a mathematical standpoint, for going through the intersections, is just like building this out in MATLAB. Yeah. Which is archaic. Don't use it.
Yeah, so for the simulation part, I'm just wondering for the like FTC case, right? So right now we're kind of use Onshape to design the 3D model of our robot. Like, are you aware of any way that we can connect that 3D model and make it like actionable within a simulated environment? Like make that robot move so that we can also do some like simple thing, like test our odometry algorithm or something like that. Are you aware of any of those platforms?
Yeah, I think the only other one that I've used out personally outside of MATLAB is the Python one. I think we've had conversations about it offline. I'm totally spacing on the name right now, but it'll at least allows you to like throw in sensors and throw on your algorithm onto it in order to like just see it working. It doesn't really have a physics uh, simulation that you can like add into it. So more of the like Unreal type stuff is not really in its uh, purview. But I still have a lot of friends doing full physics simulations, so I'm happy to reach out to them to ask for more info. I'm certainly not the most educated in this space.
Yeah, that would be great because with physics simulation, it would be ideal if we can actually simulate lots of those real stuff like friction or acceleration, deacceleration. Yeah.
Yeah, definitely agree with you. Awesome. Anything else? Any questions, comments?
So do we have any more questions? And also feel free to type in the chat window.
Yeah, thanks for reading those out too during the presentation. Sorry I missed a bunch of them. I hope we got them all though. Have we experimented with parking cars? Have not. No. That is definitely its own problem with in and of itself. Um, yeah. Sorry, don't have a more exciting answer for you, Sophia.
Okay, does anyone else have any more questions? Okay, if not, I think that's it for today. Thank you, Ray, for such an amazing presentation. I'm sure everyone enjoyed.
No problem. Yeah, thanks for letting me talk to your guys' ear off.
Thank you. Thank you.
Bye. Take care.
Thank you.
Thank you, Ray.
Of course.